And one of the types of integrals that we checked out were these types. 3x squared minus 1 all squared dx. And what we discussed previously is that we can pretty easily find the integral, the antiderivative, of any polynomial. So in order to get started, we're actually going to have to square out the 3x squared plus 1. So over to the side, I'm going to take 3x squared minus the 1. I'm going to multiply it by itself. And then let's FOIL this out real snappily. This is going to give us 9x to the 4th minus 3x squareds minus 3 more x squareds plus a 1 for a total of 9x to the 4th minus 6x squareds plus 1. What that's going to enable us to do is rewrite this original integral as something that's a little more manageable, which I'll do over here. So now we can rewrite this as 9x to the 4th minus 6x squareds plus 1 dx. And this particular integral we can integrate piece by piece. So I can take the antiderivative of this, and in order to do that I just have to write down my x. I'm going to keep my 9 out front. I know that we raise the power by 1, so it'll now be x to the 5th, and divide by the new power. For the next one, I'm going to play the same game, so let's raise the power by 1. I'll have x cubed, divide by 3 out front, and plus the antiderivative of 1 is x. Last but not least, don't forget your plus c, because you could have a constant right there. And that is the integral, or the antiderivative, of the original function right here. Now this first example, example 1, is not super difficult because squaring this thing out is just a little bit of algebra over here. Now what happens is things get interesting if I have something that looks closer to this. What if I have the integral of 7x minus 1, let's say, to, well, instead of the second power, what if it were to the 20th power? What if I were going to have to write down 20 copies of 7x minus 1 and then FOIL them all out? Oh, it would take forever. So what we need to do is develop a strategy that will help us integrate things that are a little bit fancier. Strategy that we're going to develop is something called the chain rule for integration. Okay? And just before I tell you the chain rule, I want to give you some background information on where exactly it comes from. Okay, and what we're going to do is we're going to think back to last semester when we learned how to take a derivative. And I'm going to imagine that I hand you a problem. I'm going to hand you something that we want to take the derivative. How about this guy? 1 over n plus 1 times some function, f of x, to the n plus 1. Okay. Keep in mind that n, these n's are a number like 7 or 12. And let's say last semester I handed you this function and I said, if you would please take the derivative. We go to the way inside, this f of x. Its derivative I'm going to write as f prime of x. I still have my 1 over n plus 1. It's like a coefficient. And then we know that for derivatives, we're going to take the exponent, we're going to zip it out front, and we're going to raise my guts, my f of x, to the 1 less power. So f of x, 1 less than n plus 1 is just n regular. If I simplify that out, then this n plus 1 is going to cancel with that n plus 1, and we end up with f prime of x times f of x raised to the nth power. Okay, so this is last semester. Blue function to its orange derivative over here. This semester we're going backwards. So we're starting over here at this side, and we're working our way back using integration to get to the original function. Quite possible, quite common, for us to hand you an integral of something that looks like the orange, f prime of x times the function, f of x, to a power. Okay, and because we've already worked forwards down here at the bottom to get to the orange, it's super simple to work backwards. If I integrate, if I go backwards from the orange, then I should get back to the blue. And so if you ever see an integral that has this red form, where I have somebody's derivative and then a function raised to a power, we can immediately say that that guy's antiderivative, its integral, is going to be 1 over n plus 1 times f of x to the n plus 1 plus a constant, plus RC. This chain rule is going to help us deal with increasingly difficult integrals. And what I'd like to do next is like to show you a couple of examples of how we might use this. So we want to find the integral of that. Over to the side, I'm going to write my general chain rule. F prime of x, f of x to the nth dx, and that's going to be 1 over n plus 1, f of x to the n plus 1, plus c. Okay. Now let's talk about the structure of this example. What I notice on this problem is I have an inner function, this guy right here. This is like our f of x. And what I notice, and this will happen a lot, is the derivative of this f of x happens to be sitting outside, f prime of x. That's perfect. So I have an inner function f of x, its derivative, 5x to the fourth, is sitting right here. And then I have a power hanging out here to the third power. As soon as I notice that this fits my perfect pattern over here, then I can jump immediately to my answer. That means that this antiderivative is going to be equal to my inner function, x to the fifth minus 2, that's my f of x. It's raised to the one higher power right here, so I need to take my power, raise it up there, and then I need 1 over that new, there we go, 1 higher power, and then I need 1 over that new higher power. And that is our final answer. Now what you'll notice is the f prime of x right here sort of gets absorbed into the antiderivative when we do this. And that's because if you took the derivative of this purple, you'd have to do a little baby chain rule, which would spit out this f prime of x right there. Let's look at something a little bit more intriguing. For example 2. For example 2, let's look at the integral of secant squared x times tan x plus 3 to the 7th power. The 7th power is super gross, so I'm going to cross my fingers. I'm going to hope that I have an inner function f of x. It's looking like that guy. And I'm hoping, cross my fingers, that its derivative is on the outside. So I look up here and I say, well, is the derivative of tangent plus 3 secant squared? Yes, indeedy it is. Whew. Crisis averted. So the derivative of tangent is secant squared, there it sits. As soon as I notice that I have a chain rule pattern for my integral, I can jump to my answer. So let's rewrite the guts, the f of x. I have to write it to the one higher power, so it needs to be to the 8th power, times 1 over that new higher power. Hang your plus c out the end. Notice again that the f prime of x gets absorbed into the integral. It doesn't show up in our antiderivative answer. And we're done. Example 3 has a little bit of a sneak to it, but luckily it's not too bad. Let's integrate this guy. We've got the integral of x squared times 2x cubed minus 4, all raised to the 5th power, dx. Okay, at this point I'm hoping for some chain rule. I see an inner function, f of x. I'm hoping that its derivative is out here, because that will set me up for chain rule. And I notice that if I take the derivative of this f of x, f prime of x is actually supposed to be 6x squared. And that is not what I have right here. I have only regular x squared. I need 6x squareds. We are allowed to be clever. If you notice that you have the derivative almost you're only off by a coefficient, then you are allowed to use what I call a clever value of 1. In order to help modify the f of x, the f prime of x that you have here, into what you actually need. So, we are going to be very clever, and I'm going to multiply this whole integral by 6 times 1/6. So this blue right here, 1/6 times 6, is a very fancy way to write 1, because 6 times a 6 is 1. Now guys, what that lets us do is, now that we have put the 6 in here with the x squared, now I have a perfect f prime of x. I'm very happy about this actually. And then I just have a 1/6 out front, which we'll just carry around like a coefficient. Okay, so I've used my clever value of 1 to change this almost f prime into the perfect f prime that I wanted. So now this thing fits my pattern for chain rule, and we can jump to our answer. I'm going to rewrite my blue coefficient of 1/6. Okay. I'm going to rewrite my guts, 2x cubed minus 4 to the 5th. Oh, sorry, 1 higher power. To the 6th. And then I have to multiply by 1 over that new higher power. Hang a plus c off the end. As a quick recap, this 1/6 out front comes from that part of my clever value of 1. I typically write the part that I need for f prime inside the integral and the part that I don't need outside the integral. You don't have to, but it's how I typically write it. And now we're done. There are a couple of things you want to be mindful of for clever values of 1. And the most important thing is a clever value of 1 can't have any variables. Okay. So we can have constants, we can have numbers for our clever value of 1, but we can't have any variables at all. Occasionally there's a temptation to do that, so I just want to make sure that you're wary of that situation. Let's do one more example of clever values of 1 together. For example 4, let's find the integral of 2x cubed times x to the 4th minus 3, all raised to the 10th power, dx. If I'm looking for a chain rule, I see my inner function, my f of x. I see an outer function right here. I want this to be f prime. Now I notice that f prime of x is supposed to be 4x cubes. And right now I have 2x cubes. So I'm going to use a clever value of 1. And I think that the easiest way to do this would be to take this inside part. I'm going to multiply it by a 2. And in order to make this pink equal to 1, I also have to multiply it by a half. I'm going to rewrite this integral. Have my pink 1/2 on the outside. And then this pink 2 times the other 2 is going to give me 4x cubes. X to the 4th minus 3 to the 10th dx. Now I notice that I have an f of x, and it's perfect f prime on the outside. Jumping to our answer, I'm going to rewrite my pink 1/2, so I'm not using that. My 4x cubed, my f prime, is going to get absorbed into the integral. I'm going to rewrite the guts, the f of x, to the 1 higher power, and I'm going to multiply by 1 over that new exponent, hang a plus c.